All right, so chapter 19, we're going to be looking at chemical thermodynamics, excuse me. And this is going to be somewhat related to a previous chapter, chapter 5, which was looking at thermochemistry, and that was focused mostly on sort of the movement of heat, talked about work a little bit. But if we think back to chapter 5, we talked about the first law of thermodynamics, which is just the fact that energy can't be created or destroyed. So similar to the conservation of mass, kind of whatever we have in terms of the total amount of energy throughout the universe, it's always going to be constant, but energy can move from one system to the surroundings, can take multiple forms of chemical energy, mechanical energy, whatever it may be. We can have those transfers, but the total sum of all of the energy throughout the universe is going to be constant. And then with this, we've got different types of processes that can occur. So spontaneous just means that it's pretty much automatically going to happen. We don't have to do anything extra. We don't have to put in any energy. We don't have to put in any work in order for that process to occur. So if you look at the picture on the right here, initially we've got the two flasks, and then we've got them separate from one another. So we've got the stopcock closed. We're not going to allow the two to mix. And initially, we've got some amount of gas present in flask B or vessel B, and then A is just completely empty. So it's totally evacuated. So if we open this and allow those to mix, we're going to see that the gas in B is going to flow into A. And that's going to be a spontaneous process. Once we have that valve open, there's nothing else we need to do in order for that to occur. But what we're going to see is that the reverse won't occur spontaneously. So we're not going to automatically just have A move back into B unless we do something, unless we put in some amount of work in order for that to occur. So with this, if a process is spontaneous in one direction, it's just not going to be spontaneous in the other. And another example of that is if you just leave a nail outside. So if you've got an iron nail and you just leave it outside, over time, it's just going to rust. And that's going to occur spontaneously. It's just going to happen. But the reverse isn't going to. We're not going to see that nail unrust unless something was to happen to it. We'd have to, again, put in some sort of work in order for that to occur. And with these spontaneous processes, in some cases, they'll be spontaneous at one temperature and not at the other. And in the example we see here, we actually see it kind of reversed. So on the left, we just have ice. On the right, we just have water. So if the temperature is greater than 0 degrees Celsius, for water at least, what we're going to see is it's spontaneously going to melt. So we don't need to do anything else. Just at that temperature above 0, we're of course going to see ice will melt. But then if we have the temperature below 0, the opposite is going to occur. So there's going to be a temperature dependence with some of these processes. But again, if we think about it, if we just focus on one of these for a second, so the spontaneous melting of ice, that's going to occur again spontaneously above 0 degrees because we don't have to have anything occur there. But again, the reverse process isn't going to be spontaneous under those conditions. And then just the opposite, if we're below 0 degrees, it'll spontaneously freeze, but we're not going to see it go back to the liquid water at that temperature spontaneously. So with it, and then we've talked about equilibrium quite a bit for the past like 3 or 4 chapters, whatever it's been. But what we're going to see with these reversible processes is the reason we consider them to be reversible is because we can have it go back to the original state just by doing the exact opposite. So if we look at the picture here on top, we've got the system and the surroundings, and we're seeing the heat is moving out of the system into the surroundings because we're adding heat to the system. So that's why you can see the positive delta T here. So the heat flows out of the system because remember, heat always moves from hot to cold. Cold isn't really a thing. It's just the absence of heat. But this is going to be a reversible process because if we do the exact opposite, we then remove heat from the system, we're going to see that heat flows back into it. And that's why this would be an example of a reversible process. We can do the exact opposite and have it go back to that original state. Whereas if we look at something like this is going to be an irreversible process. So kind of similar to what we saw before, we've got sort of a partition, two separate containers almost. In this case, we'll see that they can again just become one. But on the left-hand side, we just have a vacuum with a piston all the way through the end so that it can be moved back and forth to increase or decrease the volume. And then on the right side of this partition, there's just some amount of gas there. So when this partition is removed, we allow those two areas just to become one continuous unit. What we're going to see is the gas is just going to expand. And because there's a vacuum there, the gas is just going to expand without doing any work. There's nothing for it to push up against to because the vacuum is just completely empty. So we see that gas is just going to start to spread out to the left. But this isn't going to be an irreversible process because if we just do the exact opposite, if we then just place that partition back, we're not going to have a vacuum on one side and then all of the gas on the other. We're just going to have half that gas split between both halves of the container. So in order to get back to the original state in this case, we're going to need to use that piston. We're going to need to do some amount of work because we're actually going to have to push that piston in. And in this case, since we're going to be pushing it against some amount of gas, we are actually going to be doing work. So this isn't going to be a spontaneous process in that case. And it's not going to be reversible just because we can't do the exact opposite of what we originally did to get back to that original state. And again, pushing the piston against this air, if you think about, I think we had the plastics, maybe that wasn't this class actually. But with the next one here, entropy, this is going to be a key piece of what we're looking at. And entropy is going to be kind of a interesting concept. Essentially, what it's going to be representing is just the order or the disorder, more accurately, of the universe. But we'll see this equation come up a little later on. But entropy, we're just going to have symbolized with the letter S, capital S. And what Rudolf Clausius stated was that the entropy of a system, and again, we're thinking about disorder, the entropy of the system is going to be equal to the amount of heat related to that process at whatever temperature it's occurring. We'll see it's going to be a little bit different, but with entropy just in general, like I said, entropy is going to be disorder or randomness of a system. And the way that I remember when we first talked about this when I was learning chemistry, my teacher talked about just like a kid's bedroom. If you don't do anything to keep it clean, just over time, it's going to get disordered. We're going to see the entropy of that system, the entropy of that bedroom is just going to increase. It's going to get more and more disordered or more and more random. And what we're going to see is that's going to be true for the universe as a whole. The universe is constantly going to be moving towards higher entropy. But what we can do is if we focus on just a system, we can make it more ordered. So if you think about just the bedroom here, you could put in work, you could clean it up, make it nice and neat. And then that would increase the order or it would decrease the entropy. So we can put in work because that wouldn't be a spontaneous process. But with spontaneous processes, we'll see that the entropy is going to increase. And if you remember from chapter 5 or 6, whatever the thermochemistry one was, I think it was 5 I said earlier on, we had certain properties such as the energy or the enthalpy of a system that were state functions, meaning how you get there isn't important. It's just the final and the initial states that the change in those values is what we're interested in. And we're going to see entropy is going to be a state function as well. So that's why when we're looking at the change in entropy, delta S, final minus initial, like everything with delta S, or delta anything rather, is going to be final minus initial. So in this case, it's going to be the entropy of the initial subtracted from the entropy of the final. So final minus initial. And like I said, we'll see this equation a little bit later on. And we've got it here. In this case, what we're looking at is the heat associated if that was a reversible process. And this is going to be able to be used if it's an isothermal process, meaning that the temperature is going to be constant. If we've got a change in temperature throughout a process, we won't be able to use this exact equation. But to put it to use, we've got this question. So the element mercury, symbol Hg, silver liquid at room temperature, you may have seen it in certain thermometers. Typically, we try not to use it just because mercury is going to be a toxic substance. So the red thermometers you may be more familiar with typically is going to be like kerosene or ethanol or something just dyed red so you can see it a little bit better. But mercury has a normal freezing point of about negative 40 degrees, a little bit warmer. And then we have the molar enthalpy of fusion, so delta H fusion, that's going to be related to the process of melting or freezing. And then we have the value 2.29 kilojoules per mole. We want to determine the entropy change of the system if 50 grams of mercury melts at that, or freezes, excuse me, at that temperature. So with it, we'll be using this equation. Temperature, we already have. But with it, we're going to want to make sure that we have it in Kelvin. So we'll just have to convert that. We'll have to add 273.15 to that temperature. And then with the top piece here, with the Q, with the heat value, we want to remember that the enthalpy of fusion, in this case, the molar enthalpy of fusion, we've got to just make sure our units match up. So for this one, we're given grams, but we've got on a per mole basis for the enthalpy of fusion. So we've just got to convert grams to moles. So when we go to set this one up, what we're going to see, and you notice I have negative 2.29 here because we're freezing it. This is going to be an exothermic process, so we're going to be releasing that heat. So we should have a negative number there. And then, like I said, we've got to have the moles match up. So we've got to do 50 grams divided by the molar mass for mercury, so 200.6. That'll allow the grams to cancel. Moles dividing by a fraction is really just multiplying by the inverse. So we'll have moles on top. That'll cancel the moles from the enthalpy of fusion. So we'll just be left with our energy unit over the temperature. And again, we want to have this in Kelvin. That's why I'm adding 273.15 here. And if you keep it in kilojoules, you'll get like 0.00244. But I just converted it to joules here. So we get negative 2.44 joules per Kelvin. And with this negative number means that the entropy is decreasing. So this is actually becoming a more ordered system. And we're going to see that makes sense because we're going from a liquid to a solid. So we're going to have those molecules in a more rigid, sort of confined arrangement, whereas the liquids have the ability to move, to flow. So they're just going to be a little bit more random in that state. But like I kind of mentioned this a little bit earlier, but the second law of thermodynamics is just saying that entropy of the universe, at least for spontaneous processes, is always going to be increasing. So just in general, if we're not doing anything, if we're not putting in work, we're going to see that the randomness is going to constantly be increasing. And again, if you just think about your bedroom, or if you've ever been in my office, the desk I have in there is a good example of that. At the start of the quarter, typically fairly organized, but as we get later on into the quarter, just different papers, different worksheets, quizzes, whatever, labs, whatever it may be, kind of just gets scattered all over the place. And it's just because I'm not putting in the work to make it more organized. And then if I did put in the work, that just wouldn't be a spontaneous process. So that's why we can see the entropy of a system decrease, but it won't be spontaneous. And then with the reversible processes, if you think about it, the entropy isn't really going to be changing at all, because those are going to be reversible. Those can go back and forth just by doing the opposite. So in that case, any entropy gained or lost by the system, we're going to see the surroundings will be just the opposite. So the change in entropy for those reversible processes is just going to be zero. But for the irreversible ones, that's where we're going to see a larger or a positive value in terms of the delta S, excuse me. And then this I've been mentioning throughout those past couple of slides, but with the spontaneous processes, those are always going to increase the entropy, just because those are going to naturally happen without us having to put any work in. And higher entropy or more disorder is always going to be a favored state. And again, if you just think about your bedroom, if you don't do anything to keep it clean, it's just naturally going to get more and more messy. And that's the same idea with the universe as a whole, whether we're looking at something like a bedroom or my office desk, or if we're thinking about just a sample of some substance as well. And then with entropy, we're going to be able to, in some cases, like we just did, sort of calculate a change in entropy, put a numerical value on it. In other cases, we're going to be focused sort of on a more qualitative sort of analysis. So in terms of just, does entropy increase or decrease, stay the same? And with that, we want to think about all of the different types of motion that a molecule could undergo. And with it, we just want to also remember that temperature is going to be a measure of average kinetic energy. So as the temperature increases for a sample, the energy of motion, which is what kinetic energy is going to increase as well. And then with that motion, we've got several different types. So translational is probably the most thought about, most common type of motion, because that's just simply going to be sort of moving from one spot to another. So if we had a gas sample, for instance, those molecules are going to be constantly just sort of zipping around. And that would just be translational. So as we have higher kinetic energy, as we have higher temperatures, they're just moving around faster. But what we also have with these molecules is going to be vibrational and rotational energy, or rotational and vibrational motion, rather. And if you look at the picture here, the first couple show those vibrations. So that's essentially showing how the atoms are kind of moving almost with respect to one another. So if you look here, the atoms themselves are going to be kind of moving closer and farther away, those bonds. You can see here, this one moves to the left, and then in the other case, it's moving to the right. And sometimes we have them go sort of side to side. So it's going to be the movement of those atoms within a molecule. And then the rotational motion is going to be a little different. In this case, we're thinking about a sigma bond, so the single bond. What we can actually do is kind of take the atom there and just spin the whole molecule around that point. And as we have higher kinetic energy, as we have a higher temperature, we're going to see we'll have more of this, all of these types of motion. And then I forget if I mentioned, what was this person? Ludwig Boltzmann. So Ludwig Boltzmann just kind of came up with this idea. So we've got these different types of motion. And I like the term snapshot because I think this picture here does a pretty good job. We've got all of these different types of motion. So if we just looked at a molecule and then took a picture of it 1 second and then took a picture of it the other, we're going to have a potentially a different, what's known as microstate. And what that's referring to is essentially just all of these different possibilities. So if you look at these, this could be a water molecule, for instance, and all of these would be water molecules, but they would each have a different microstate just based on the vibrational and the rotational motion that we're exhibiting here. And what Boltzmann was able to do was able to come up with an equation to calculate the entropy of a system. So K is just going to be what's known as Boltzmann constant, so just named after himself, 1.38 times 10 to the negative 23rd joules per Kelvin. And then the natural log of W is going to be referring to all of the different possible microstates. So like I said, each of these would be different microstates, and then there would be all the other possibilities as well. So what we're going to see is as the number of microstates increases, the entropy will increase as well. And with that equation, if we go back for a second, we have the natural log of W. So we can kind of take the properties of logs. If we've got the natural log, and we're looking at the change in S now. So it's going to be that same equation from the previous one, but it's going to be final minus initial in terms of the number of microstates. We can then rearrange that to just be just dividing those two. Because remember, subtracting logs is the same as dividing. But like I said, the big thing here is the entropy of a system is going to increase with the number of those microstates, just because we're going to have more possibilities for the different setup. We're going to have more randomness within that system. And with those microstates, we're going to see the number of them is going to increase with the higher temperature. So we're going to have them moving around faster. We'll have more vibrational and rotational motion. So we're just going to have more microstates. Same thing with volume. If we allow everything to expand more, it's going to have more space to fill in. So we're just going to have more microstates because of that. And then the more independent molecules we have, the more microstates we'll have as well. So the more entropy. And with that one, we can think about the phases of matter. So with the gases, all of those molecules are essentially going to be independent of one another. So they're going to be able to move around. It's going to allow for more possibilities, more randomness. With liquids, they're still able to kind of flow over one another. There's still some motion there. And there's still motion with solids, but with the liquids, they can, like I said, still flow. So there's still going to be more possible microstates. And then with the solids, if you think about it, something like this could be water, or these are water molecules. So when we freeze them, we're going to have a more rigid arrangement. There's going to be less flexibility within those molecules. There's also going to be a lower temperature. They're going to be in at least for most substances, the solid's going to be in a smaller volume. It's going to be a lower temperature. They're going to be more rigid in terms of their arrangement. So for several reasons, we're going to see solids are going to be the lowest entropy, and then gases on the other end would just be the highest. And then with solutions, so we've got the aqueous, and we could have the same thing with different types of solvents as well. But if we focus on an aqueous solution, particularly with an ionic compound, what we're going to see is, in general, the entropy is going to increase. But we can kind of look at this from two different perspectives. We can look at it from the perspective of the ionic substance, or we could look at it from the perspective of the water. And what we're going to see is the opposite is actually going to happen. So with the ionic substance as a solid, of course, we're going to have the rigid arrangement. We're going to have sort of that crystalline structure. But when we dissolve it, now we have those ions separate. So that's going to increase the number of microstates. It's going to increase the entropy with respect to the ionic substance. But now with the water molecules, what we're going to see is those actually become more ordered, because you can kind of see from this picture around the positive ones, we've got the red negative oxygen surrounding it. With the negative ones, we have the opposite occurring with the positive hydrogens. So when we have a solution created, the water generally becomes more ordered, so the entropy decreases, where the ionic substance becomes less ordered, more random, the entropy increases. So we've kind of got those two competing factors. But in general, the disorder of the ionic substance is going to be greater than the ordering of the water molecules themselves. So typically, dissolving a substance will increase energy or increase entropy, because of the ionic substance is going to sort of take precedent almost over the water. And if we think back to a couple of slides ago, we said gases are going to be higher entropy than liquids, which are going to be higher entropy than solids. We can think about the phase changes. So if we take a solid and sublime it, or if we take a liquid and boil it, we're moving into that gas phase. We're going to see the temperature is going to increase. We're going to have more possible microstates just because those molecules are now going to be independent of one another for the most part. They're going to be occupying a larger volume. So for multiple reasons, we're going to see going to the gas phase is going to increase entropy. If we melt a solid or if we place it into solution, like we just saw, that's going to increase entropy as well. And if we just increase the number of molecules overall, that'll typically increase entropy as well, just because we'll have more possible microstates. We'll just have more things to kind of have organized or disorganized. So with the last couple of yeah, so we'll just look at these final two slides in this video. And it's just going to be looking at trying to determine how the entropy is going to change throughout these reactions for the first one. And then the second one, we're just going to think about two different samples under similar conditions. So take a second to kind of go through these four. And the first one, we're taking liquid water, turning into water vapor. The second one, we're having a precipitation reaction occur. Third one is going to be a combination reaction. And then the fourth one will be a combination reaction as well. So take a moment to just pause the video, kind of think through them yourself. But with these ones, again, we want to think about the state of matter. We just want to think about the randomness of these samples in general. A positive delta S, so an increase in entropy, is going to be representing a increase in disorder, an increase in randomness, while a negative delta S would be the opposite. So for the first one here, liquid water to water vapor, get the pen thing, find it, there we go. What we're going to see in this case is entropy is going to increase because we're going from liquid to gas. So we're going to allow these molecules to spread out more. They're going to be independent of one another, so they're going to have more freedom. Basically, we're going to have more microstates. Because of it, we're going to see the entropy is going to increase, while the next one is going to be the opposite. If you think about it, in this case, we're taking two ions, combining them to be a single molecule. So we're going to decrease the freedom of each of these ions when they're combined as the precipitate. And just in general, like we said on the previous slide, going from solid to liquid or solid to solution is going to increase entropy. So if we're doing the opposite here, we'll see a decrease. And then with the final two, we're going to see a decrease there. And for this one, it's going to be due to the fact that we've got, if you think about it, 7 different, if we're just thinking about like atoms or molecules with these coefficients rather than, or we could think about it as moles, but atoms and molecules, that's smaller numbers, a little bit easier to wrap your head around. In this case, we could have 4 iron atoms and 3 molecules of oxygen. So we've got essentially 7 things here. And the oxygen is going to be a gas. Whereas the product, now we're going to have 2 molecules of iron 3 oxide, and it's going to be a solid. So we're going to have less freedom just in general with these substances. And we're just going to have less molecules overall. So we're going to see a decrease there. All right. And then the Final one here, I'm actually just going to put 0 because it's likely not exactly 0, but it's going to be a very small entropy change, whether it's positive or negative, just because we have the same number of molecules on both sides. So if you think about it, N2 plus O2 gives us 2NO. So we've got 1 molecule of nitrogen, 1 molecule of oxygen, 2 molecules of nitrogen dioxide, or nitrogen monoxide rather, and everything's gas. So the number of things isn't really changing at all. They're all still gases, so there likely is a entropy change overall. But with this information, we can't say for certain whether it's going to be positive or negative. So we would just say, and I'll put the little squiggly equal sign. Whoops. Let's pretend that I wrote that well. Let's pretend that looks like a squiggly equal sign 0. And then with let me clear this. With the next one, kind of just do the same thing. Pause the video, give yourself a little bit of time to kind of think through these. But with the first one, we've got a mole of sodium chloride solid versus a mole of hydrochloric acid as a gas at 25 degrees Celsius. And we're just focused on the state of matter for this one, basically, because we've got 1 mole of each. They're at the same temperature. We've got 2 atoms in both of these substances. But since the hydrochloric acid is a gas, we'll see that's going to be a higher entropy. And then for the second one, we've just got more of that gas. So we've just got more possible microstates. We're going to have a higher entropy in that case. And then with the final one, we've got 1 mole. They're both gases. We've got them at the same temperature. But with it, since the hydrochloric acid has more atoms, we're going to have more microstates, whereas the argon atom is just argon by itself. So if you think about it, there's going to be no vibrational or rotational motion there. It's just going to be translational, basically, because it's just that one thing by itself. There's no bond. So the HCl should be greater there in terms of the entropy. And then with the, oops. With the next video, we'll start to look at the third law of thermodynamics.